Our next speaker is Dr. Neeraj K Dhanwani from IISER Mohali, and he will be speaking on Quandles arising from surfaces. Yeah, over to you, Neeraj. You may start.
Thanks for this opportunity, and sorry for this inconvenience. And I don't know, there's some problem with my devices, and maybe I'm not that good with
It's
the
fine.
devices. Okay, thanks. So today's my talk is based on mostly on the Quandles, and for this talk, I will only try to talk about those Quandles which are coming from the surfaces. But again, in between, we have to go here and there to make things work. So let me firstly start with surface. Though mapping class group is discussed in both the talks, not in very exactly the sense, but in anyway. So again, fix the notation for the talk purpose. Like SG is a closed surface with oriented surface genus G. You denote the homeo plus SG with all the orientation preserving homeomorphisms of surface SG. And you define the mapping class group as all these homeomorphisms up to isotopy. You can define up to homotopy. They are the same equivalent definition one can do. Anyway, so throughout this talk, whenever I talk about the surface, my target surface is always a closed orientable surface. That means genus is this is always SG. Then no puncture, neither boundaries. So all the definition, all the work can be generalized there, but avoid the technical risk. And mapping class group for the sphere is actually just identity. So things are not very helpful there. So mostly we will work G greater than equal to 1. Okay. Let me define the other term of my talk, the Quandle. A rack is just a generalization of it. Anyway, Quandle is a non-empty set Q together with a binary operation. The operation satisfies these properties. The first property, that is idempotent. That means x star x is have to be equal to x. Second, for each x and y in Quandle, you can always find a z such that x equal to z star y. And this z have to be unique. Third is some kind of distributivity. It's saying x star y star z is equal to x star z star x star y star z. This three definition is those very algebraic. Nothing seems from here that why these are important, but these are very important. At least nowadays, a lot of research going on, especially on these properties. Anyway, second property. If you see, it's telling something about the function. It's telling z can be thought of the something inverse of y. This is actually telling me the the action of y can be reversed also. I will define it more precise in the future, but firstly, this is just a definition. Whether we have some examples. So yes, the first example is very easy. You can just take a group G and you define the operation star as a conjugation. So you define x star y is equal to x y inverse. So y is acting on the x and giving a conjugation. This is the first example which easily can see that is forms a Quandle. The second example is again coming from the group. A group G with a binary operation defines something like this. X star y equal to y x inverse y is called a core of the group. These two operations are coming in the group. When particularly you take group to be abelian, mode cyclic abelian group, Zn, then this particular class is known as a dihedral group of order n, which is coming by the cyclic n. But again, there are more other examples, which are some of them coming from the group, some of them may not coming from the group. You can define just by hand. But still, why we study this? Like, is there some applications, motivations. So the one more example, let me talk, which is the make this area to completely in the fire, like many people comes on this way because the relation with the links. So for given any link, you can define a link Quandle. So for those who don't know what is a link, let me just define in a vague terms. A link you can define as embedding of the disjoint union of circles in R3 up to some equivalence. This embeddings, we instead of understanding them in R3, we understand them in the R2, looking their planar diagrams, planar images. So for the example, to say, see examples, these are the two links we are uh, keep in the mind whenever we are thinking. First is a torus knot. It's the smallest, simplest knot one can think. In the first knot, we have only one circle. This is connected, but in the second half link, we have two circles. One can, like, the k is equal to 2 here. Now, this is a link or not. How you connect the Quandle here? That's a key idea to making this field great. Like, okay, so whenever you have a knot diagram, locally at every point, this look like a crossing. At every crossing, you define a relation like this. So incoming x, overgoing arc y act on x, and the reproduce the arc is as x star y. Whenever the is a positive crossing, and for negative crossing, you define x star inverse of y. Star inverse is just a inverse of the star operation. It's allows me this by the second property that you can define such a way. So now this operation, this Quandle operation is actually these three properties of the Quandle was very natural, and they are coming via the Radmaster moves. So this Radmaster moves is actually this up to isotopy I talked. The mapping class with some the knots up to some equivalence. So this three moves is actually the equivalence. What are they? They are the first type of move is this. Whenever your knot is have something like this loop, you can reverse the loop and make it a straight line. The second, okay, firstly, how you define the operation here. So you define all the terminology x, then on the joint, if you see on the joint, it is x is overpass, is also the undergo arc is also x, so x star x. But when you remove this, the x star x have to be x, which is the giving me first relation in the Quandle, first axiom of the Quandle. The second axiom of the Quandle is the x star inverse y star y is equal to x. So this z which we have chosen, which was a unique z for given x and y, is actually x star inverse y, which is just a algebraization of the Radmaster second move. And Radmaster third move tells me whenever two arc, the third arc is behind the first two arcs, you can move at the same level in the z-axis. So this is just sliding the third arc, blue arc, and that's giving me a third axiom of the Quandle. This was noted in the in 1980s by two different authors independently, that this Quandle structure is actually classifying the knots up to the mirror image, which is the biggest problem in the knot theory, to classifying the knots. So it's a complete, almost complete invariant for the knots, but at easy. So this makes a more to understand the Quandles. What are the Quandles can be associated with the links, and when you can understand them completely. Okay. So with these examples, now we are more interested to define some more terminology. In the first example, in the previous example, we saw that Quandles arising from the groups. But there is a way to associate the groups to the quandles also. So first is inner automorphism. So how you define the inner automorphism? Said by the use the second axiom. Given every y in the quandle Q, you can define the inner automorphism Sy as this. Sy acting on X is X star Y. This obviously gives you the automorphism, and this automorphism we call the inner automorphism. Similarly, you can define other automorphism, and whole group is called the automorphism groups of the quandle Q. The other group you can define is the enveloping group. This is some most of the like literature is called a structure group, adjoint group. This called adjoint group because on the group correspondence, this is the adjoint functor. If you have a group, you go in the conjugation quandle, and from quandle you go to this enveloping group. They are the adjoint functor on the categories. But anyway, we don't need that much stuff. So how you define the enveloping group? Whenever you have a quandle, for each element of the quandle, you define the element here in the generating set, in the enveloping group EX, and the relations you define whenever E of X star Y, you define it as EY, EX, EY inverse. So whenever there is a star operation, you change the star operation by the conjugation operation. And this was again nice result in the same paper where the quandles and knot theory composition defined by the Maldiv, and the other paper was by. So in their paper, this shows that this enveloping group for the knot quandles, whenever which are the quandles coming by the knot, this enveloping group is as a fundamental group of the knot in the S3, S2. Now let me come to the topic. Come to those quandles which coming by the surfaces. Any question till now? Okay. So firstly, you have a surface SG, closed surface genus G. Now you take the collection. C is a collection of simple closed curves. On this collection, you define the operation by how the one curve is acting on the other curve, and for that you use the Dane twist. So Dane twist is defined in the previous talk. Let me define again. For given a curve A, whenever the another curve is coming near to the A, what you do, you cut along the A, rotate the surface, and glue it again. So your surface will look like something this. Your curve B will now be the rotate along the A and look like the TAB. So this is a Dane twist, and this under this operation you define A star B is equal to TB of A. To defining the Dane twist, you need a simple closed curves, and thus are required in this all the collections. Under this operation, this collection be a quandle. This is very natural construction. In particular, when you take a non-separating simple closed curves, this collection is again forms a Dane quandle, and most of the time we will only focus on this quandle. Okay. So till now the definition, what the initial results we have in this direction, the Yetter, firstly in 2000, even this Dane quandle appears before Yetter also in the Jablow's thesis, but Yetter was the one who studied this quandle structure, homological quandles especially, to understand the vibration of the surfaces. If you know this terminology, great. If not, just if Jablow in 2008 come up to the more great idea to understand the homology of these quandles, especially for this Dane quandles, and he shows then that some co-cycles have something related to the vibrations again. In the 2009, Brzezinski and his collaborators shows that the Dane quandle of torus is actually the isomorphic to knot quandle for trefoil knot, and their presentation is given by this. This was again a very motivating for the many other researchers to look at whether there are relation between this knot quandles and the Dane quandle which are coming by the surfaces. In the another paper, he shows that no, it's not actually. This is something very special, but there are still some results known. In the 2014, again, Jablo studied this Quandle to understand the geodesic foliation, major geodesic foliation on the surfaces. So this Quandle, though look like a very algebraic structure, they have a lot of geometric information that make us motivate to understand this Quandles more in the algebraic sense. Okay, so now whatever I talk, it's based on these two papers, which are my joint work with the Professor Mahendra and my collaborator Dr. Hitesh Chandal. So let me firstly define this Dane-Quandle structure in any general setting. So if you take a group G and take any subset A of the group G, then you consider all the conjugacy classes of the elements of the A. You can define the Quandle structure on this set AG by the just a conjugation operation. Because you already chosen all the conjugacy classes of A, under the conjugation, they will remain in the set. So this and conjugation is already satisfied the Quandle operation, Quandle axioms. So this forms a Quandle, and we will denote it as a DAG, Dane Quandle of A corresponding, Dane Quandle of group G corresponding to subset A. This is motivated by two different construction, actually the free Quandle and the Dane Quandle of surfaces. How I will define in just a second. But firstly, for the Dane Quandle, these three conditions are equivalent. Firstly, whenever the Quandle embeds inside the conjugation for any group, then that's a Dane Quandle. That means you can find something subset of H such that this can be written as a D of AH. Embedding means you have injective homomorphism, Quandle homomorphism. Second, the natural map eta from Q to enveloping group is injective. The third condition is you can always find a group G and S such that Quandle is isomorphic to this. Now, what are the examples for the Dane Quandle? For very obvious purpose, you take any conjugation Quandle and take any subquandle of that is going to become a Dane Quandle. For perspective that conjugacy classes, you pick the representative. Second, this was appeared in the 2021 by in some paper in the Wegerman that the core Quandle can be visualized as a subquandle of the conj Quandle, which tells us the core Quandle can be visualized as a Dane Quandle. The third example tells this is a classical result of the Ryder which appears in 96 that given any knot is prime if and only if the knot Quandle embeds in the enveloping group, and which equivalently you say the knot is prime if and only if knot Quandle is Dane Quandle. The fourth example, which is our focus example, is the Dane Quandle of the surfaces. How this you can be seen as a subquandle of the conjugation Quandle. You take the conjugation operation on the mapping class group and define every curve as this Dane twist. Again, all the three properties of the Dane Quandles axioms actually they is actually easily hold by the basic properties of the Dane twist. One of them is previously talked in the class. The previous lecture is actually you take the conjugation of the Dane twist is again going to become a Dane twist along the curve under that homeomorphism under which you are looking the conjugation. So now you can see the Dane Quandle of surfaces as two different ways. Either you can visualize them as only subclasses of the curves and the subclasses of the conjugacy classes of the Dane twist. So my time is over, but I haven't reached anywhere. So can I take a few more minutes as I lost some minutes early?
Yeah, maybe 5 minutes. Yeah.
That's it. So G is a group and S is a generating set. Then for Dane Quandle is generated by the set S. If S is a generating set of the G, and that will tell me for my Dane Quandle of the surfaces, because they are visualizing them as a Dane twist level, and Dane twist are the generating set for the mapping class group. Using the result of the licorice, we can say that for this Dane Quandle are non-separating Dane Quandles can be generated by these many curves, and these are minimal because these are the Humphreys set of the generating set. Anyway, I'm not telling why this is true, because this result by the mapping class group. Other result is actually this Dane Quandle is not only algebraic properties holding, it's somehow capturing the geometry also. So whenever your intersection is 0, they satisfied some very particular relation A star B equal to A. That means B does not non-trivially act on the A, just giving only A again, and B star A is again B. And similarly, whenever intersection is 1, they will satisfy some particular type of relation, and this is a if and only if. Whenever they satisfy this relation, the curves have to be satisfied the intersection number 1. This is a geometry, and other side is your algebraic condition. The proof is just reading the facts of the basic properties of the Dane twist in the Quandle level. Other proposition is telling me whenever you have a geo, that means they together forms a trivial quandle. Trivial quandle means one is acting on other as a trivially action. For the intersection 1, they will always form the one quandle, which is a profile, the Dane quandle of the profile node, and this always embedded. One can always embed this in the any Dane quandle. For the intersection, whenever intersection is greater than 2, the Dane quandle is generated by them is actually the free quandle. What about the automorphism group? You can say the automorphism group, for the automorphism group, we can say that for the given group, and whenever you are looking for this, inner automorphism group is always a group quotiented by the center. But for the whole automorphism group, you have to work little hard. And for the free quandle, this is a very classical flavor in the welded weight group theory, and that's started a new field completely. But in the mapping class, whenever you have dealing with this Dane quandle of surfaces or conjugation quandle of mapping class group, one can prove that the automorphism, the whole automorphism group of Dane quandle of non-separating curve is actually same as the inner automorphism group for the z greater than equal to 1 and mg quotiented by center. But the center of the mapping class group is trivial whenever g is greater than 3, so it's exactly equal to the mapping class group. Okay, now let me come to the another topic. Whenever you have an algebraic structure, it is interesting to see how you present this structure. This is the second work, and for this we come up with two different ideas. One of them I am discussing here. So whenever you have a group and you are considering the Dane quandle of that corresponding to this generating set, you have a presentation of the group and use this presentation to construct the presentation of the quandle. How? You consider the central, you can take an element and look at the centralizer of that, and for them you define this some functions. You define the text set T as all the S and comma T, the pair which are the conjugate, and F as a map from T to S, which satisfied these three properties, which is just conjugation properties. Is obvious, like you just need to. So using these properties, how you define, you can come up with a presentation of the quandle. So you take all the S element of the S, because that's all again going to generate your Dane quandle also. What are the relations you are looking? So relation is writing the relations of the group as a terms of the quandle. The first one is whenever you have a relation in the group, you write as a conjugation operation under the quandle until it have to be trivial, act trivial on the S. By the way, whenever I'm not writing the brackets, this is always acting by the left because this is a non-associative algebra. The second, you take the centralizer of the X and tell every generator of the centralizer is act trivially on the S. And third is relate the conjugate element by the elements. Though this theorem was, the proof is really easy. Just go step by step and check this. All the operations have to be satisfied in the quandle, and whenever this relation satisfied, these are the good enough to satisfy any relation in the quandle. But the come up was a good thing, and this idea behind this was a very hardcore Garside and Garside theory and the groups, Garside groups, but I'm not going in that way. Okay, so we can use this theorem to give the presentation of many interesting quandles. First is the dihedral quandle, which is the smallest and very important quandle for us. The presentation of that quandle can be given based on n is even or odd. So for the an odd is this presentation and an even is this presentation. What is getting by this? The first result, whoever know the knot theory, is knot can be colorable. And whenever you called about a colorability, you actually color by looking the homeomorphism from the knot condyle to the dihedral condyle, and using that structure, we can say whenever you have a torus knot T, Mn are the co-prime and N is even, then is always M colorable. Not only is M colorable, you can choose all M colors. That means you can particularly choose all the elements of the dihedral. We can retrieve the result of the Prisisky and tell the Dane condyle of the torus is again the trophile knot of the knot condyle of the trophile, which the presentation is this. For this, you just need a centralizer of one Dane twist, which can be easily computed for the torus because it's SL2Z. For genus 2, the work is little hard because there are more relations and the centralizer is little tricky, but one can compute and is already known in the literature by the work of Putman. The centralizer of any Dane twist for the first Dane twist can be given by this, where I is a hyperelliptic involution. And using this relation, you can come up with a presentation of the Dane condyle of genus 2 is by this, which is the generating set of 5 element and the relations are this. Okay, let me stop. Thanks.
Yeah. Thank you, Neeraj, for the nice talk. Any questions? So I have maybe one question. So you're calling this core, right? Core of this. So why is this like?
Yes, yes.
So there is one concept called normal core of a group. Is it related to that or?
What is the normal core of the group?
Normal core of a subgroup is basically you take all its conjugates and then take intersection.
No, actually, I'm not aware. Like, no, it's not seeming to me interconnected, but yeah.
Okay.
I don't know why people call it core.
Nice.
But this is a very used terminology. Many articles use it. Maybe it's good. I will check in the literature who first called it core and why they called it.
Right, right. Yeah.
I will get back to you.
Any other questions?